So we are going to discuss about the foliation. So first of all, let us draw space-time volume V. So a space-time volume V is actually, as we had discussed, is this generic surface. In which this one is the three-dimensional hypersurface sigma T2. This one is the three-dimensional hypersurface sigma T1, and as we remember, these and this is the generic hypersurface sigma T. We remember that delta V is actually sigma T2 union of minus of sigma T1 union of this curved time-like hypersurface curly B. And why this minus sign? This minus sign is basically due to the nature that our NA is always defined to be future pointing, and sigma T here, I mean the normal to this sigma T actually points outward, which is in the past pointing direction, and hence we have to incorporate this minus sign to have a consistent nature. And the boundary of the closed boundary of this generic three-dimensional hypersurface sigma T is denoted by ST. So ST is the boundary of this, and where the time-like hypersurface curly B is actually the union for all the values of T of ST. Good. We remember now we will talk about the foliations of this. I mean, we already know about the 1 plus of 3 foliation of the space-time volume V, and we'll talk about it a bit. But then after that we are going to foliate, that is 1 plus 2 kind of foliation of this curly hypersurface B. So this is going to be the main objective of this. Okay, so let us recapitulate a little bit, in the sense that we talk about the 1 plus 3 foliation of V. That is, V is actually, that is the space-time volume V is actually foliated by these stacks of hypersurfaces sigma T, and this is our, I mean these are our generic hypersurfaces sigma T. So let this be sigma T, let this be sigma T1 T prime, for example. And how did we foliate that? We foliated it by we foliated the space-time by these stacks, or by these families of stacks of hypersurfaces parameterized by this value T, and we had this time evolution vector T, which is a set of congruents that connected equal spatial points. That is, this point P, let me make it capital P, and this point P prime have the same spatial values on the hypersurface sigma T. For example, if this point P prime has the coordinates, has the spatial coordinates yi, then P also has the spatial coordinates yi. And the only parameter that increases along these congruences, which we do not assume to be globally hypersurface orthogonal, the only parameter that changes is the value of is the parameter value T. which is given by the obviously which is given by the scalar functional of this, the scalar function of these hypersurfaces. Good. So any point on the hypersurface, so the coordinates xa of v can actually via this foliation be broken down as the value of t comma yi. So this is our foliation of 1+3 foliation of the the space-time volume v. Okay, this being done, now what we have is that now what we'll do is that we'll construct this we'll have a 1+2 foliation of this curved surface B. So what exactly is this curved surface B? This curved surface B is actually these stacks of two surfaces, two-dimensional surfaces ST. So this is for example ST1 and this is ST2, and this is a generic two-dimensional hypersurface ST, which is actually the boundary of sigma t. And the way we foliate this curved surface B is via these stacks of two-dimensional hypersurfaces sigma t. So we'll assume that the intrinsic coordinates, let me briefly also mention about the coordinate system that we are using. So it's good to have a mention over there. So our space-time volume V is actually parametrized, or is actually coordinatized via xa. And once we have introduced the 1+3 foliation via these stacks of hypersurfaces sigma t, then xa can equally be interchanged by the value of t comma yi. Our sigma t, which is actually a three-dimensional space-like hypersurface, is actually coordinatized by the set yi. This two-dimensional hypersurface ST, which is actually two-dimensional, will have the intrinsic coordinates. Let me denote them by theta a tilde. Okay, so these are the intrinsic coordinates, and let the intrinsic coordinates on beta, curly beta, which is a three-dimensional time-like hypersurface, let it be coordinatized by y mu. And we'll see once we include this, once we perform this 1+2 foliation of this curly surface beta, B, we can exchange y mu with some sort of analogy like this. But we'll see how we can do that. And it's pretty straightforward in that sense as to how we can do that. But before doing that, let me talk about the embeddings of ST in the space-time volume V. Okay, so we'll talk about first ST, which is a two-dimensional surface as viewed as as an embedding in the four-dimensional space-time volume. Okay, good. Just let me grab 1 second. So this is our ST, which is the two-dimensional surface, and the unit normal that points outside of it is denoted as RA. Okay, and how do we parameterize S of t? So S of t can be denoted by a scalar function capital psi, which is a function of this yi on sigma t being equals to constant. Okay, so the parametric curves on ST will be given by yi is a function of theta a tilde. Okay, and in the same way, this can be expanded to x of a being a function of y of I, which is a function of y of I function of theta of a tilde. So we have x of a being a function of theta of A tilde. These are the parametric curves on ST. So the normal vector RA of ST is actually proportional to del A of psi as we know it. And okay, so this is the normal vector. We'll have to determine the proportionality constant, but that can be easily done. We'll talk about the tangent vectors on ST. The tangent vectors on ST are given by this, which is actually equals to del XA divided by del theta A tilde. And we can have a nice form of writing down these tangent vectors on ST. So we have EA of A is equals to del XA divided by del theta A tilde is equals to del XA divided by del YI divided by del YI of del theta A, which is actually equals to EI of A EA tilde of I. So this is actually the tangent vectors. So what exactly is this? This is this EIA is the tangent vector to sigma t, and this is actually again the tangent vector of the tangent vector of ST as viewed from the three-dimensional surface ST. So see the point is that ST as a two-dimensional submanifold can be seen as an embedding on the three-dimensional hypersurface sigma t, or it can be seen as a two-dimensional submanifold embedded in the four-dimensional space-time space-time volume V. So we have that the tangent vector on the two-dimensional hypersurface as seen from the four-dimensional space-time is actually equals to the tangent vector on sigma A times the tangent vector of ST as viewed from the three-dimensional submanifold. Good. So similarly, we can have this RA, which is actually the unit normal to ST, can be expanded in the basis vectors of ST, can be expanded on the basis vectors of ST, and we know what the basis vectors of ST are. The basis vectors of ST are these exactly. So we can have the basis expansion of RA to be equals to RI, these are the components, times EI of A, where EI of A are the the basis vectors of sigma t. Good. Okay. So let me proceed. So what is the induced? So once we have defined, defined this normal as well as the tangent vectors, our next step is to define the induced metric. The induced metric on the hypersurface two-dimensional submanifold ST is actually as viewed as an embedding, from the three-dimensional surface. Now it is going to be a lot of mixture, but let me restate. Right now we are going to talk about the induced metric of the two-dimensional submanifold ST as viewed as an embedding in the three-dimensional hypersurface sigma t. And what will it be? It will be equals to Hij EAI EBJ. And we know what Hij is as seen as an embedding in the four-dimensional space-time. So it's going to be a hodgepodge right now, but I hope you can understand, and you must actually. Let us combine these. So what we have is sigma A tilde B tilde is equals to GAB EA tilde A EB tilde B. Good. So this is our definition of sigma A tilde B tilde. Now we have defined our so you can see that we have so we can see that we have defined our the induced metric on the two-dimensional submanifold ST as viewed as an embedding in the four-dimensional four-dimensional space-time volume V, right? So again, let us go back. We have the three-dimensional covariant derivative of the outer normal Ri to the two surface St, where Ri is obviously a spatial vector. This is obviously again a spatial vector of St, and so this covariant derivative does make sense. This three-dimensional covariant derivative as defined, compatible with the compatible with the hypersurface sigma t, is well defined, and we have that this is equals to del B of Ra EJB EIA. So obviously you can know that, and our extrinsic curvature, sorry, not intrinsic, but rather extrinsic curvature, kappa A tilde B tilde of the surface, the two surface ST as viewed. Now let us go step by step. As viewed as an embedding in the three-dimensional three-dimensional surface sigma t is equals to del J of Ri on tilde I EB tilde J. So this is our definition, as viewed as an embedding in the three-dimensional sigma t. But then we can again convert it back to as seen as an embedding in the four-dimensional just by these formulas, which is equals to del B of Ra EJB EIA EA tilde I EB tilde J. Let us combine these. Which one should be combined? This one and this one, and this one and this one. So this will turn out to be del B of Ra. What will be this? EA tilde of A EB tilde of B. Good. So we have now a formula for the extrinsic curvature of the two-dimensional surface ST as viewed as an embedding in the four-dimensional space-time volume capital V is given by the formula del B of Ra times EA tilde A EB tilde B. Very good. So we have got what we have in a sense desired. it took us some time, but it's clear, right? So this is an embedding of ST as viewed on this in this four-dimensional space-time volume. Okay. Again, let us write the completeness relation. The completeness relation Hij of the three-dimensional hypersurface sigma t is given by Ri Rj plus of sigma A tilde B tilde EA tilde I EB tilde J, and our GAB is actually equals to minus of NANB plus of Hij EIA EJB. Now if we put this formula of Hij into this, it's very easy to show, and I leave it for you to check. It's quite evident also. You should be familiar with it right now. It's quite understandable. from the study of null hypersurfaces that you have done. So what you have done is that you have broken it down. You have broken this 4-dimensional metric GAB into a 2-dimensional part, a 1-dimensional part, and a 1-dimensional part. So this is in a sense an essence of 1 plus 1 plus of 2-dimensional, 1 plus 1 plus 2 decomposition. So this is the completeness relation for that. Very good. Now we'll talk about the foliation. We'll talk about how to foliate this curly, hypersurface, time-like hypersurface, beta. B. I shouldn't be calling it beta, but rather it's B. Okay. Hold on a second. So how do we actually define our curly hypersurface, B, which is actually a 3-dimensional time-like hypersurface? It will again be defined by some scalar function. Let us call it psi of capital psi. I don't know what it is called in Greek symbolism, but let us say capital psi of is equals to some 0 for for the curly hypersurface B, and the parametric relations that define the curves exclusively on this hypersurface beta will be given by x of a is equals to x of a of z mu, where z mu are obviously the intrinsic coordinates on B. So we have B coordinatized by our set z mu. Good. So first of all, let us talk about the tangent vectors. The tangent vectors to the curly surface B. It's given by E mu of A, which is equals to del XA divided by del Z mu. Right? What is the normal? The normal to B, since B is actually the union for all the values of t belonging to t1 to t2 of st, the unit normal to B is actually the same as the unit normal to S, which is equals to Ra. So we have the unit normal. So the unit normal to St and the unit normal to this curly hypersurface B actually coincides, which it should actually. There is no other way. Good. So once we have defined the tangent vectors and once we have defined the unit normal, we can define the induced metric on beta. The induced metric on beta is given by gamma mu nu, and gamma mu nu is equals to GAB E mu A E mu B. Now let us talk about the extrinsic curvature of beta. The extrinsic curvature of beta will be denoted by this curly K mu nu. K mu nu is actually equals to del B of Ra E mu of A E mu of B. And what is the completeness relationship? The completeness relationship is GAB is equals to RA RB plus of gamma mu nu E mu of A E mu of B. Now once we have analyzed this hypersurface, analyzed this 3-dimensional hypersurface curly B, our next job is to foliate B with our construction of the family of two surfaces ST. So there's actually no need to, because we already, by our construction, we already have foliated B with these by these families of these two surfaces ST. But we have to make a proper choice of coordinatization once we have foliated. So we'll have to introduce again a set of congruences that traverse across tangentially, that traverse across this hypersurface curly B, such that they will connect space-time points that that they will connect the spatial points on ST. I mean, let me phrase it again. So we'll construct a set of parameters. I mean, we'll set up a set of congruences on this curly hypersurface B that will, that will take or traverse along which the same spatial points of ST will traverse. I'll draw it. To make it more clear. So we have so this is our 3 surface beta. Okay, let us, okay, and this is our 2 surface ST2, this is our 2 surface ST1, this is a generic surface ST. This is let us draw another one. This is our generic surface ST prime, and let us draw curves right now. These will be the congruences of curves that will actually transform spatial points, that will actually transform the same spatial points on on the hypersurface. In a sense, it should be evident before we said that, for example, the intrinsic coordinates on a particular ST is given by the set of coordinates theta a. Now suppose we have another adjacent surface ST prime where the intrinsic coordinates are again some theta a delta. It does not have to be that these should be the same as this. For example, this can be parameterized by theta and phi coordinates, this can be parameterized, say, x and y, this can be parameterized by, say, x and y will be fine, or y and z. So it does not need that, it does not need to be that, the coordinates on one boundary surface ST has to be the same on the coordinates on another boundary surface ST prime. But it will be convenient if we could do so. And the way is that via these congruences, let these congruences be denoted by some beta, because we have already used gamma for the congruences that cut through these surfaces sigma t, but now we are talking about ST. So these curves, let us talk about this particular curve, and this is given by P, this is given by let us talk about P1, this is P, this is P prime, and this is P2. So let this curve be beta P. So what beta P does, okay, before we say so what we say is that this curve beta P actually translates the same spatial points along this curve. For example, if P1 has a spatial coordinates theta a tilde, so does P, so does P prime, and so does P2. All these have the same spatial points, just like we did for sigma t as well. But now there's a catch here. There's a certain simplification that we are using, is that these curves beta P are hypersurface orthogonal. That is, we demand that these are perpendicular to these surfaces ST. Good. But this is a certain imposition which we have for the foliation of ST, which we did not impose when we talked about the foliation of sigma t. there are the evolution vector that connected the same spatial points was the t vector, and t vector was not the same as the normal, but here the normal to the st surfaces actually carry out, actually transport the same spatial points along along the normal to st surface, along the normal to the st surface. Okay, good. Now once we have defined that, so these congruences, again in a sense, let the vector field that defines these congruences beta p be denoted by some v. So we'll have that the Lie derivative along this vector field v of these tangent vectors Ea tilde of A should be equals to 0. This denotes the fact that these spatial points are translated along these along the vector field v, which is actually the integral curve, the integral curves of which is beta p. Okay. Now, as you can see that the tangent to the curve beta p is given by del xa del t, keeping the values of theta a fixed. So this is actually the tangent to these curves, beta p, which is denoted by some e t of a. And by our construction that these congruents of curves beta p are hypersurface orthogonal, it implies that it should be proportional to NA, where NA is the normal to the two-dimensional the boundary surface ST. So we'll have to find out what this normalization factor is, and it can be easily done so with the fact that NA is equals to minus of 1. Okay, so we have that NA is equals to 1 by A of del xa del t theta a. At the same time, we have NA is equals to minus of NA of del A of t, where t, as you know, is the scalar function defining the surface sigma t, is equals to minus of del of xa of t. So we have 1 by A of del xa del t of theta a minus of n del t of del xa is equals to minus of 1, which implies that A is equals to n. So you have that NA is equals to 1 by n of del xa del t, keeping the values of theta a fixed. Right? Very good. Okay. Let me just mention here that Et of A is actually equals to n of NA. Now we have done our basically the foliation, and also to mention, also you should notice that these curves beta p, the parameter that we can choose, the parameter that flows along these curves, that flows along these curves beta p, to be actually t itself, because for example here the value of t is t1, here the value is t, here the value is t prime, here the value is t2. So the curves beta p also, analogously to the curves like gamma, could be parameterized and should be, it's a very convenient choice to parameterize it by the by the parameter value t. So now we have that the intrinsic coordinates za, once we have done this 1 plus of 2 decomposition, can equally well be broken down or chosen to be the coordinates t and theta a tilde. So this is another choice of the the foliation under our choice of foliation. Under our choice of foliation. So any arbitrary displacement dxa that is confined on the surface curly, on the boundary surface curly b, is actually equals to et of a dt plus of ea of a d theta a, and I hope that you can easily understand why it is so. I don't need to go ahead with this. So this is equals to n of na dt plus of ea tilde of a d theta a, where I should mention that remember that these are the tangent vectors on this surface st. Okay, so let us construct the metric on entirely on the the hypersurface beta, which is equals to gamma mu nu dx nu is equals to gab dxa restricted to b dxb restricted to b, and let us input these values on dxa, and if you expand it, it will be very easy to show that it is equals to gamma mu nu dx nu is equals to minus of n square dt square plus of sigma a tilde b tilde d theta a d theta b. So this is our decomposition of the metric, 1 plus of 2 decomposition of this metric as per our foliation. And again, it's very easy, just like the one we had done for the 1 plus of 3 foliation, to show that the square root of the determinant of the metric on this curly hypersurface B is actually equals to the Laplace function times the induced metric. I mean, this is actually the induced metric on the two surface ST. And finally, let us talk about the extrinsic curvature. The extrinsic curvature of this this three-dimensional hypersurface curly B, as we had shown, is equals to del B of R A, E mu of A, E nu of B, and the trace of that is equals to gamma mu nu, K mu nu. It's quite evident, as you should know. So this is it. So we have had three types of extrinsic curvatures, right? We have the extrinsic curvature KAB of sigma t. We have the extrinsic curvature kappa AB of ST, and we have the extrinsic curvature curly kappa curly KAB of the curly hypersurface B. So we have in essence done our foliation and all these things. That will be it, and after this we are going to talk about the gravitational action and how we will decompose the gravitational action in the spirit. I mean, we will decompose our the bulk term of the gravitational action in the spirit of 1 plus of 3, and the boundary term, and the because remember the gravitational action had a bulk term and a boundary term. We will decompose the bulk term in the essence in the spirit of 1 plus of 3 decomposition, and we will decompose the boundary term in the spirit of 1 plus of 2. That will be our next topic, where we decompose the gravitational action in the spirit of this formalism. Okay, that will be it. Thank you.